Hello, Mr. Collier here. This is your first set of notes on nuclear chemistry. So a nuclear reaction, which is one of the main things we'll be talking about in this chapter, is one that changes the composition of an atom's nucleus. That nucleus is held together with something called the strong nuclear force. Because if you think about it, normally in a nucleus, there's these protons, and protons are positive, and like charges repel. So those protons are trying to push each other apart, but they're held together by the strong nuclear force. Most atoms are stable, so the combination of protons and neutrons and the strong nuclear force makes them stay together in a stable configuration. However, those tend to be the smaller atoms, which are not radioactive. As atoms get bigger, many of them become unstable. They just have the wrong mix of neutrons and protons. We call these isotopes radioactive. Typically, as elements become larger, they become more unstable. However, every element has at least one radioactive isotope. And every isotope of every element bigger than 83 are all radioactive. These larger isotopes are radioactive because they just don't have that stable ratio of protons and neutrons. So here's a little graph that illustrates what I was just saying. Here on the x-axis we've got the number of protons, and on the y-axis we've got the number of neutrons. Now for these light elements we tend to have about the same number of protons and neutrons, but then it starts going off, right? This green line here is your 1-to-1 ratio, 1 neutron for every proton. But what we start to see is that for an element to be stable, it starts to need more and more neutrons, which kind of act like a buffer for those protons that are trying to repel each other. And eventually we've got as many as 1.5 neutrons for every proton. And right around 80, like I was saying, we start to hit completely just unstable atoms, where while those atoms exist, none of them have stable nuclei configurations. So I want to talk about what types of radiation can occur. So first, some background information. You've got protons and neutrons, right? And they can actually be a type of decay. So you can actually have atoms lose individual protons and neutrons, although that's not what we're going to talk much about. And they both have a mass of approximately 1 atomic mass unit. Protons are positive and neutrons are neutral. And then there are 3 types of radiation that we're going to talk about: alpha, beta, and gamma. Beta particles are basically electrons. Alpha particles are basically helium nuclei, and gamma is not a particle, but rather an energy. Beta particles, because they're an electron, have a -1 charge. Alpha particles, because they're made of protons, have a positive charge. And gamma rays are also neutral. They're just energy rays. The symbol for a proton is P+, or you can write it as H1/1. H because it has a single proton, right? That is what hydrogen is. And 1 because its mass number is 1 because it's just a proton. Neutrons can be written as N0, or N with a 1 on the top and a 0 on the bottom, right? 1 for the mass number, 0 because there are no protons. Beta particles, which are just electrons, can be written as a -1, or you can write it as a little beta symbol. Alpha particles can be written as helium because they're a helium nucleus, or a little alpha symbol, and they have a mass number of 4, and 2 of them are protons. And finally, gamma rays are just energy, so you can write them as either an E for energy, or this little sort of Y-looking thing that is the symbol for gamma. Now, these different types of radiation can be stopped by different substances. Some of them are much more penetrating than others. As you can see, alpha is the least dangerous, easily stopped by like your skin or a piece of paper, whereas the most dangerous is gamma radiation, requiring something very thick and heavy to stop it. And here's an illustration of what I was just saying about what it takes to stop different types of radiation. So, unstable nuclei will spontaneously emit 3 types of natural radiation. This is also called radioactive decay. When it emits radiation, the original nucleus decomposes or decays to form a new nucleus and releases that radiation. This can be written as a nuclear equation. For example, the nucleus of an atom, for example, here's radium, might decay in such a way that it gives off an alpha particle. An alpha particle is 2 protons and 2 neutrons. So by losing an alpha particle, an element's atomic number actually goes down by 2, in this case from 88 to 86, because it has lost 2 protons. Its mass number will go down by 4, because it's lost 2 protons and 2 neutrons, making its mass number decrease by 4. And so this is what the equation for alpha decay looks like. You start with an isotope. You end with an isotope that's always smaller because it's losing an alpha particle. Beta decay is an interesting one because by losing an electron, it actually makes the atomic number go up by 1. What happens is that a neutron turns into a proton, essentially, by emitting an electron. So one of these neutrons actually becomes a proton, but the total mass stays the same because it was a neutron, but now it's a proton, both having a mass of 1. So this is how you then write your beta decay. You're always going to have the atomic number go up by 1, and you'll have your beta decay. Mass number stays the same. So to summarize that, we've got alpha decay, which spontaneously emits an alpha particle. So in alpha decay, you're going to have the atomic number go down by 2 and the mass number go down by 4 with the alpha decay written after it. So here's an example. See if you can figure it out. We've got silver with a mass number of 185 and an atomic number of 79, and it's emitting an alpha particle. So we know that its atomic number will go down by 2 and its mass number will go down by 4, which leaves us with iridium element 77 with a mass number of 181. So radioactive decay can literally turn one element into a different element. Here's beta decay. Here's an example. Carbon is going to go through beta decay, and it will actually become the next element up, nitrogen. Its mass stays the same though. Or it might look like this. We have an element, it goes up by 1, right, from iodine to xenon, and that must mean that we're going through beta decay. The last type is gamma decay, and gamma rays don't actually change an element. So you start and end with the exact same element with the exact same atomic number and mass number, but energy has been emitted. Gamma decay can also accompany other types of decay. So you might have alpha decay and also some gamma. You might have beta decay and also some gamma. The gamma decay just kind of lets you know that this was a very energetic thing and some dangerous radiation came off it. But in terms of the actual equation, it doesn't really mess with what element you have. So this diagram pictures how these radioactive decays react to different charges. So for example, alpha particles are positive, so they are drawn toward a negative plate. They're drawn not so much because they're a heavy particle, whereas beta decay is negative, so it's drawn toward the positive plate, and it's drawn more dramatically because it's a smaller particle. Gamma decay is not deflected at all by charged particles because it is not charged. And here we have a graph that shows that as carbon goes through beta decay, nitrogen starts to appear. So we might title this graph The Effects of Time on Carbon-14 and Nitrogen-14 Concentrations. And one last thing to close on. Elements can go through a series of decay called a decay chain or a decay series. And so you might start with a heavy element like uranium, and it might decay into thorium, and thorium might go through a couple terms of beta decay, becoming actually a higher atomic number. But then we might hit a couple strings of alpha decay in a row where the atomic number goes down. And this can continue, alpha and beta making the atomic number go up and down until eventually things that are going through radioactive decay will settle on something that's stable. So this is lead. And lead is actually a very common element for radioactive things to settle at. It's a stable isotope, and it's kind of the heaviest one. And that's your introduction to radioactive decay.